Welcome and thank you for downloading the SteerDev podcast.
Okay. Before we start, I'd like to know, to ask, did you all register and enroll for the course on Blackboard? Can I see hands, please, who enrolled for the... Okay, that's good. And the books, that's a more difficult one. Who has got the book already? Because I've heard yesterday from the VSV. Okay, great. I also saw a lot of hits on the site, but if you didn't, I'll show you briefly where you can find everything. Most of the information regarding the course is in the course information, under the course information. This is how it looks for me. Maybe it looks slightly different if you're a student, but I think overall it will look the same. And then you get different folders. We are currently working on Module AB. And then inside Module AB, you'll find some information, including notes, solutions and balloons, handouts of balloons. But all the stuff that they hand out can be found there. Somebody asked, can I also see what the homework was? I didn't put it up Blackboard. I will next time. I will make sure notification giving the exact homework, but also note it down because sometimes it takes a little time. The slides are not on there yet. You do not run in parallel with the Dutch group exactly, so I'll put them up when both audiences have seen the slides. Then I'll put the slides up, but all the other essential information will be put up there as quickly as possible. Regarding the homework, some asked yesterday if it's mandatory. No, it's recommended. If you have any questions regarding the homework, you can approach me before the lectures or during the break. If I notice that there's something really unclear to many people, then I will explain this in the plenary sessions, but I will not go into the details of the homework right now. So, let's quickly see what we did yesterday. Yesterday we basically started off with the traditional formula as you use them in high school for the gas law and gravity, but we basically transferred them to a different shape. We use the gas law as what we call equation of state. Pressure is the air density times R times T. Be aware this is not the R that you used in high school. This is not the 8.3145. This is the 287 R of specific for air. And here you see if you talk about different gases in general, you would write it as such. But by default, in this course and all the aerodynamic courses, the R is always the R specific for air, for the mixture of gases that air is. We're also not using this one because this is not very handy, so we use the hydrostatic or aerostatic law. That's basically our law of gravity. So yesterday we already made a quick start with the hydrostatic law, which is the basis of our standard atmosphere. But before we continue with that, I'd like to go into a standard atmosphere or the atmosphere in general. And if we look at the... No, I'm at the wrong slide here. So if we talk about the atmosphere, it's very important for us to know the characteristics of an atmosphere. Different screen. So we have a short look at that. We also saw that you could get really high with a helium balloon and a camera underneath, as we will do again this weekend with the students from VME. But you could also go there yourself, of course, if you put yourself underneath a balloon. And there were, in the 60s, there were some experiments called Excelsior 1, 2, and 3. And at one point, they sent somebody up high, really high, with a helium balloon to test whether you could jump from this altitude, basically in preparation of ejecting from high-altitude aircraft. And it's really fascinating to see. I'm not going to run the complete video right now, but you can when it's on the Blackboard. It really is like space. He needs a space suit and everything, and he was really a daredevil that he went to do this. He went higher and higher in stages. They did it 60,000 feet first, and later went to 100,000 feet. At some point, he had a problem. We will calculate later, remember this altitude, what the circumstances are that high in the atmosphere. How close is it really to space? Is there still a lot of air around, or is it really nearly vacuum? Of course it is, if you compare that you already need oxygen mask at 8 kilometers altitude, Mount Everest. It is really, there's not a lot of oxygen there, and also not a lot of pressure, I can tell you already. We'll see the exact numbers later. But to give an impression, at one point he had a hole in his glove, Mr. Kittinger, and that was, of course, not a good thing, because then the finger underneath is exposed to vacuum, nearly vacuum. But it seems that the human body has a protective mechanism for that, because the finger was swollen to twice the size that it had on sea level, and in this way it closed the hole of the glove and solved the problem. Mr. Kittinger also lost consciousness at some point. He is one of the few that has gone through the speed of sound without any equipment, just by himself. Luckily he regained consciousness again later, so he could open the parachute in time. Also note that when he ascends from sea level, the helium is very minimal compared to the maximum volume that you need in a balloon. One of the favorite exercises that we can do where we combine the balloon and the atmospheric circumstances is that you can calculate the maximum altitude of a balloon based on the maximum volume of a balloon. So here the maximum altitude is determined by when the helium volume has expanded to the size of the balloon, and then it will burst and you will go down. Let's see if we can get to where he jumps. Here he's really high. Sky is already black and he still needs to go higher because this was still recorded from an aircraft. It's an open gondola. And this is about the highest step on Earth I think you can make. And there he goes. And you could also see, if you watch very close or watch again close at home, you can see the way he moves, that you can really see that there's no air resistance, because even if he's already falling very fast, you can see him moving his arms and legs very quickly. And this is zoomed in again, him falling very deep. Somebody even made a song about it, and that's added as a soundtrack to this video clip. Okay, but the real atmosphere is very different. Here we see the measurements Tim Zaman made with his balloon, the camera, and he recorded the altitude, but also the temperature inside his little, well, satellite nearly it is, because there's a lot of, it's similar to what you do in space. And you can see that the temperature, which should go down very quickly, doesn't really go down. It's really stays around 20 degrees, and only here it really goes down, the temperature, and you can see that the altitude also goes down. So apparently he had a lot of insulation, and only when it started falling, the insulation didn't work anymore, so sort of chill factor or a lot of air going through the material, because then only the temperature was dropped. If you look at what weather balloons register, they have different temperatures and pressure every day. So this is, for instance, you see different measurements on the same day even, with different weather. So you cannot talk about what the pressure at a certain altitude is. You need some reference, some average. Why would we need a reference? What would be the reason that you need a common reference? To do simulations, that's one. Yeah. Other reasons? Yeah, check your answers. Well, reference also implies, of course, that if you say a certain aircraft can reach a certain altitude, that it means the same to everybody is an important reason. So you need a common reference to specify aircraft performance, and you also need something indeed for our calculation, for our modeling, analysis, and simulation. You also need a lot of assumptions. If we set up our model atmosphere, we cannot just assume a certain pressure, temperature, and air density. They need to be physically correct, but there are more assumptions that we need, because with the real atmosphere, we saw that the temperature is higher at lower altitudes. And normally, high temperature air wants to rise, wants to be above the cold air. And which means you get convection in the lower part of the atmosphere where the temperature is still decreasing. And that's normally, we don't call this convection normally. Normally we call this weather, because that's basically the engine that drives our weather, the convection in the troposphere. You also can see that in the troposphere, the temperature is nearly constant. And even though here it's hard to see, but you can see that it doesn't change as much anymore. It really goes to a sort of vertical line. In the standard atmosphere, there is a vertical line in the troposphere. This means that there, the air doesn't rise anymore, and also means there is no weather there. So one of the reasons why it's nice to fly in an airliner through the troposphere, through the stratosphere, because you fly above the weather. And of course, there's less drag with lower air density. So here we see the reasons. We also needed to define air data calculations, for instance, what a speed means or an altitude means. We use the air pressure in an aircraft to measure the altitude. And this is not the correct altitude that we measure. It's nearly always wrong. But as long as everybody uses the same reference, the same pressure altitude, at least we make sure that when somebody says he's at a different altitude, that he will miss the other aircraft, because they're both wrong in the same way. So that's another important reason to have a common reference, that you need onboard calculations for your altitude, which are the same for every aircraft. So this is this standard atmosphere. You see it here. We already went through the layers yesterday, the ozone layer, and then again it gets higher there. Here you see the different layers. For our calculations, a lot of flights still take place in the troposphere, but you will occasionally also see the stratosphere with aircraft, and with balloons you even go higher. You go to past the 32 kilometers. Well, to model a standard atmosphere, we want it to be physically correct. So what we basically have to do is we have to treat it as a real atmosphere and then set the minimum amount of parameters. Well, we saw yesterday that we have two laws and we need to set three quantities. So this gives us 1 degree of freedom. And that's why we can choose the temperature. And that's what we do based on our day-to-day experiences, and we have a sort of average. And it was the first one to decide what that was going to be was Mr. Toussaint, a Frenchman, who said, on average, in the lower part of the atmosphere, the temperature decreases with 6.5 degrees per kilometer. And this was gradually adopted by everybody as the sort of standard for the lower part of the atmosphere. This was the first definition of the standard atmosphere. But of course we want to know how to calculate this. And these formula don't do that for us yet. I mean, the top one you can use. If we know 2 parameters of these, we can calculate the third one with it. But we still need something more if we know the temperature of how to calculate, for instance, the pressure. And from this, the air density. Well, to be physically correct, it has to obey those 2 laws. So let's use those to set up our model atmosphere. We have seen in this slide on here that we have basically two types of layers. We have layers where the temperature has a linear gradient, a fixed gradient, a linear distribution, and there are parts where it's 0, which we have to treat as different layers. So let's look at what happens if we model this atmosphere. We see the notation here for the D, the differential equation, dP and dH, and we said yesterday this refers to an infinitesimal small disk. So if we want to make larger steps through the atmosphere, what we need to do then is to sum all those little parts, and that's what we do with the integral. You have seen in high school the integral, you've probably seen it defined as the area underneath the graph. But that's just one way to say it, because basically if what you've done so far is calculate this integral, and this is the same as fx dx, and that is indeed the area under a graph, because what you basically did is you took very small steps in the x direction and multiplied this with the local value of y at that point, and this way you calculated the area underneath a graph, a to b. So the integral sign itself doesn't really stand for area under a graph. It's basically a summation sign, a summation of all the little parts that go behind this. So if you sum all these bars, if you sum all the y dx's, then indeed you do get the area underneath the graph. Well, we have the d sign for the dp and dh in our hydrostatic law. And so if we want to make larger steps, we need to do the same. So if we want to know the pressure difference over a large step starting at 0, which we also need to fix, and I gave the values yesterday. So at 0 altitude, we have a P0, which is 10132.5 Pascal. We have a 0 temperature, which is 15 degrees Celsius, which is 288.15 Kelvin, and we have a rho 0 of 1.225 kilogram per meter cubed. So this is what we set as our starting point for our model atmosphere. Then we said we know the temperature. Temperature at altitude is starting temperature plus change of temperature times the altitude, with the A being 0065 Kelvin per meter. Normally it's given as 6.5 Kelvin per kilometer, and often made mistake by students at the exam is that they fill in this value in the formulas and getting very strange answers, but still go on. So always check the SI units. And this should be a minus sign, by the way. It decreases because I've put plus in the formula. 6.5 degrees per kilometer. And Kelvin, a degree Kelvin and degree Celsius is of course the same if you talk about relative temperatures. So this is the temperature. The temperature we know then for the first layer. But now if we want to use the integral and sum everything for dp, we run into trouble because we do not know what will happen if we go from 0, P0 to P1. We go from H0, which is 0, to H1. And then we have a problem because the density will vary with pressure, and we don't know the density, because if we would have known the density, we would have known the pressure as well, together with the temperature. So here we need to change it to include something that we do know, which is the temperature.
Sir,
yes?
what is the
Second
second altitude versus H0?
altitude is the altitude of which we want to calculate the pressure. H1 is what it meant to say here. So we want to go from making a larger step, from all the small steps to a larger step, and we need to go to a certain altitude which we call H1. So by this we will derive a formula for deep pressure at the altitude H1. Can you see what you're writing, or is this better? So everybody got this? So we need to change the hydrostatic law. Well, this is the hydrostatic law. If we also know that P is rho RT. In other words, rho is equal to P divided by RT. If we substitute that, then we get an equation of T and P, the one that we don't know, P, and the one that we know, T. So we get minus pressure divided by RT times G times dH. And here we can now move all the unknowns, the p's, to the left side, and what we know, leave that on the right side by dividing by p. So if we divide it by p, we get 1 divided by p times dp is minus g. Well, this looks better. Now all we need to do now is to make sure that we have, instead of the t, we have the h, or instead of the h, we have the t, because those two we know, and then we can solve it. Well, we had the formula th is T0 plus A times H. And here, A is the temperature difference per altitude. So you could say it's the temperature difference per altitude difference. In other words, the H is the temperature difference divided by A. And now we're getting somewhere, because if we fill this in, one divided by T, Tt. We can write it as such. So I've moved the A to the first, because it's a constant. I've moved it to the first factor. Here is the A, and here's the dt. So this is dt divided by A, which is the same as dh. And now we've made it more, now we can use the integral finally, because here we've got only p that varies, and we've put it as a function here, and here we've got t. So if we then take the integral from our 0 altitude to the altitude that we want to know, we can say we go from P0 to P1 with this integral. This is all constants, G, A, and R, so we can move that in front of the integral. From T0 to T1, 1 divided by T times dt. If I do something strange which you don't understand, just say so and ask, because just writing it down is not enough. Yes? From this to this? Well, I basically wrote G divided by R times 1 divided by T. In that way I split this off. And I replaced dh by dt divided by A. So that's how I got the dt here and the A there. So basically the A ends up here because I used dt instead of dh. So speak out a bit louder, I can't hear you. How do I get to 1 divided by t? Here, this is just from this to this. Well, divide by t or times 1 divided by t is the same. So I just split it off of this. I split it off here, and then I go here. So that's the same t all along, and you get it because of this. Okay? Is it really clear? Because we're going to continue now. It's just by moving around the different factors in the denominator and the other part of the fraction. If it's not clear, say so. I'm happy to. Okay. Yes? Shh. The first, what? The top ones. That's what we explained yesterday. That's how we got those are basically taken from yesterday. So the left one is the hydrostatic law, and the right one is the gas law. Okay, so now we can solve this integral. On the page with high school stuff you need to know, you also saw the integral of 1 divided by x, and that is... Say again? The natural logarithm. Yeah, exactly. So here, if we solve this integral, we get basically ln p1 minus ln p0. And we get the same on the other side. So that's how the natural logarithm comes in. And then, to make this look a bit better, to get rid of the logarithms, we do everything to the power of e. So this then becomes e to the power ln p1, ln p0. E, I should add here, ln t1 minus ln t0. So we do both left and right, we say to the power, e to the power of what was standing there. And that we do because e to the power ln x, of course, equals x. So that's how we can get rid of the logarithms, which we don't like. So if we do this, we also know from calculus that if you have a to the power a minus b, that's equal to this goes for any power operator. So this is how we first can get rid of this. We can basically say it's the same as e to the power ln p1 divided by e to the power ln p0. Oh, too fast? I should make 2 columns and then be able to move it to the side, right? But it's not that fancy. Okay, I have to move on now. So what we end up getting on this side is then these two. This way. Shh, if you have a question, please stop me. But otherwise, and we also saw on the right side, we saw e to the power gar times ln t1 minus ln t0. And here we cannot immediately do this, but there's another rule which basically says e to the power p times q is the same as e to the power p to the power q, right? That's just that you can multiply if you have to use the power. So here this means we can change this left side now to p1 divided by p0. And here we can do the same trick with the temperature. And then we end up with this to the power. So did you see what happens here? I reverse the 2 factors because it's a multiplication, so I can just as well put them on this side and this on that side, the minus gr. Then I did the same trick as I did with the pressure, so that's how I get the fraction, but I still have to multiply it with this, or if I look at the doing it to the power, I have to put this in the exponent of this fraction. Well, this is something we can use from day to day to calculate temperatures and pressures at a certain altitude. Because we know the temperature that we started with, we can easily calculate the T1 with the linear formula using the altitude minus 6.5 per kilometer. Then we have the temperature at the altitude. These are all constants that we know. We fill those in, and then we get the fraction of pressures. We knew this one, and we know that one. So how we normally use this is simply by calculating the pressure. P1 is T0 plus A times H divided over T0, the power of minus AR, times P0. And that's how we normally do it. And there we have the formula for a pressure at any given altitude in the troposphere. For the air density, we can basically substitute rho 1 R T1 divided by rho 0 R T0, which is basically the same as P1 divided by P0. And this is still equal to T1 divided by T0 to the power of this exponent. Then we see that basically we see the same R here, so we can take away that one. And then we see here T1, T0, which we want to move to the other side. So we divide by T1 over T0, which means this exponent will be reduced with 1. So this means for the density, the formula looks very similar, but this still has an important difference. It's T1 divided by T0 minus G divided by AR minus 1. And here again we can calculate the T1 by filling in this formula, and in this way we can immediately calculate the air density at any given altitude for any layer which has a linear change of temperature. And then we have a physically correct atmosphere if we do that. Yes? First you, okay. Here. How do I do that? What I do, I multiply left and right by P0, so this is how I get here. And T1, I just fill in the T0 plus AH. Say again, what happens in the last move here? The minus 1. So here we can take away the R, this is the same. And then we divide, both sides we divide by T1 over T0. So we divide by this fraction, and dividing by it is the same as lowering the exponent of minus 1. So I could also say I add times T1 divided over T0 to the power minus 1. And then you add the two exponents, and that's how you end up with the minus 1 there. Can we get rid of the minus 2? Yes, of course. If we revert those two, we can get rid of all the minuses. That would also be a nice touch. It's commonly used as this one, maybe to avoid errors that you fill in the wrong temperature or something. If you use this formula, there are some steps with exponents and things you have to calculate. Always check whether the numbers that you get, whether they look real to you. So if you suddenly get a higher air pressure when you go higher, something must be wrong. Or if you get strange temperatures or strange exponents, but often do those things. I sometimes see people continue with the strangest answers, maybe out of despair, I don't know. But still, if you see an odd number, check your calculations and make sure that it makes sense. So get a feeling for these numbers. Next week at the instruction session, we will also have an exercise in which you need to do this with numbers. Then you will get a feeling for it. And also later, we will go through different layers, and then you will also see some numbers in the next hour. So this is for a gradient. Of course, there are also the isothermic layers, isotherm layers, where we have constant temperature, and then this doesn't work. We've done two things which should make us cautious. A bit quiet, please. If you have a question, raise your hand, and otherwise, just wait. You can also ask me in the break. This is of course the other computer. What we've done here, we have to be careful. What we did here, we put the G in front of the integral sign. But in real life, the gravity acceleration reduces when you go higher. So we made a small error. You can read on in Anderson and also on the handout what that error is. And this means that this assumption of a constant gravity acceleration basically means that we have not used the real altitude. So the altitude that we have here is called the geopotential altitude, and it's called h, and we use this as if it were the standard altitude. But be aware, there's always a small error, but it's negligible small, so it's really very small, and that's why we are, as engineers, say, okay, as long as we all use the same altitude, we make the same error, that's okay. But check out what the difference is, and you will see that it has to do with the altitude compared to the radius of the Earth. So that's why it's very small. The other thing that we did is that here we're divided by A. So there you can also see that if there is no change of temperature, this doesn't work because we cannot divide by A. We cannot divide by 0. So what happens if there's a constant temperature? We have to step back then to the very beginning of these calculations. And we have to go back to basically 1 divided by P over dP is dH. This still holds. This still works. So then we have to see what happens then next. Basically, we say the temperature is the same, so that has become a constant. So basically, we can immediately go to the integral here, and we say P1 to dP is just minus GRT, which is now a constant, and we go from H0 to H1 times dH. So here we get again the logarithms. And here, what's the answer to the integral on the right side here? H1 minus H0, that's right. H1 minus H0. Because the primitive function of 1 is H, and so we fill in H1 and H0 and subtract H0 from H1, and this is how we get this. So then again, if we now use, to get rid of the ln, take to the power of e, you get P1 over P0 here, and here we get e to the minus . And this is indeed the formula for the pressure change in a isothermal layer. Be aware that here P0 and H0 refers to the start of that layer. So it means that because the atmosphere is made of different layers, we have to step through the atmosphere per layer. So you start off with sea level, then you go to the first layer, and then your indices sort of shift, and then the base values for your next layer are used in this formula as the reference values, as the 0 values. I'll show you later how this works. But here we can also see what happens to the density then here. We can again fill in P1 divided by P0 is equal to this. Should be equal to the same formula again on this side. Well, in this case, it's much simpler because not just R is constant, but also our temperature is constant. So this means it's the same. So the same value goes for the ratio of densities as for the pressures in an isothermic layer. So this is much simpler. This fits on one page. So this is how we do it between 11 kilometers and 20 kilometers. Between 11 and 20 kilometers for every layer where the temperature is constant. There are 2 layers, in fact, if you remember correctly. From the chart, there were 2 layers where the temperature is constant, the inversions. It's basically, if you see here, I'll put the other one back up in the break. Here you see the first layer from 11 to 20. Here you see it again, the second, and here we never fly, but there's a third one even there. And these 2 are what you most commonly experience. Very often we fly in the stratosphere, so you first then have to go from 0 to 11 kilometers with the first set of formula, and then you have your starting values for the next phase, and then we use the second set of formula for this layer. And sometimes if you have to go above that, we even have to go on in the other direction. Okay? So let's keep a short break at this moment, and then in the next hour, we'll use an actual example and calculate the amount of air that Joe Kittinger had in his gondola. Continue. Okay. Two remarks. First, about the error that we made regarding the gravity acceleration, assuming that it's constant. Here you see, if you would do it actually right, you would use the actual g, which would also be a function of h, of the altitude, which would complicate the integral and make it only solvable numerically, which is not very handy if you want to make analog instruments, even though today's computers could probably do it. So that's why we simplified it by using the g0. I wrote g all the time, but basically we used the constant g at sea level. And then we just call this altitude, we just give it a different name. So we call the actual altitude is the geometric altitude. That's the correct altitude, the real altitude. And we use the index g for that. hg is the geometric altitude. But by default, we will from now on use the geopotential altitude based on the calculations for pressure, and that's we call h. But just in the back of your head, remember that it's the wrong one, but if you see that at an altitude where we rarely fly, 63,000 feet, the error is only 0.3%. So that's why we think it's acceptable to do it as such. But one of the questions could be is explain the difference between geopotential and geometric altitude and derive the relation between geopotential or geometric altitude. And then you have to answer something like this. Oh my God, well, it's not that hard. It's pretty straightforward, actually. It's simpler than the other ones, I think. So you would be lucky if I asked this. Be aware that the derivation is part of what could be asked at the exam. It's not just to explain where the formula comes from. We want you to be able to derive these equations for two reasons. First, to understand what's going on, but also as a sort of practice, because in later years you have to be able to derive such formula yourself. For two reasons. One is that you could be in some project or assignment where you need to derive something new. And the other one is to save memory space in your head, so that for the exam you only have to remember a few formula and you can derive the others. And that's the only way to survive, because as you will see, the amount of formula quickly accumulates. So you really have to see it as a sort of web of different formula which are all related, and you just pick your nodes, the ones you want to remember, and then you want to make sure that you can derive the other ones. So practice it a bit. The first time it looks very hard, and then you find out that there are just a few hurdles. If you remember those, it's very straightforward. One of the things that I notice every year is that the way we use integrals or differentials is still, for some people, new. Apparently it has to do with also wiskunde B, as it is taught in high school nowadays, doesn't pay as much attention on integrals and differentials as it used to be. So the ones that also had wiskunde D should have it easier. I know also the Belgians have it easier. For them, this should be relatively straightforward. But this is something you'll have to get used to. And otherwise, refresh your memory by looking up the integrals. Just revisit them quickly. Here are some basic integrals. And I'm also using the area under the graph explaining why you go from x to half x squared, for instance, or how I went from dh to h1 minus h0. That's basically the integral of the function 1. And if you see this 1 times the x as the area underneath the graph of the function 1, you can easily see that this area is 1 times the horizontal, which is b minus a. And same goes for from x to half x. If you look at the function x, y is x, this has to be a straight line, it's meant to be a straight line, then you can see that the area is half the rectangle here which has the sides x, because y was x, and then half, so x times half. And this is why the primitive function of x is in half x squared. And in the same way, all the functions are derived. You can also remember if you take the derivative of this function, you end up with this one. So it's inverse derivation, if you will. So that's what we used, and that's how we got from 1 divided by x to the ln of x, which is the primitive function of 1 divided by x, which is basically the definition of the number e. So let's use this. For instance, we saw Joe Kittinger jump from an altitude of, what was it, 31? So let's try to calculate p, rho, and t at an altitude of 31.3, or comma, I should say, if I use the Anglo-Saxon notation, meters. That's also something we should be aware of course. If you look at the English exam, we use the comma to separate the powers of 1,000. So this is not 31 meters, which you wouldn't need a parachute, but it's 31,300 meters. So this should be at, okay. So we want to calculate p, rho, and t at this altitude. So if we look at the graph of the atmosphere, you see we have to go through a number of layers. So we'll take them one by one. So the first layer is the troposphere, which runs up to 11 kilometers, which has a lapse rate of minus 6.5 degrees per kilometer, and starts off with 15 degrees Celsius, 288.15, and this pressure. You also see that we end up above the 20 kilometers, so we have first to go to one layer, then we go to another layer, and then we end up somewhere in this third layer. One important remark is that if you look in chapter 3 of Anderson, he uses a completely different atmosphere. There are two standard atmospheres in the world. There's the international standard atmosphere, and there's the United States standard atmosphere. And Anderson doesn't use either of them. He has a very old one, because in fact the standard US standard atmosphere has gradually over time has merged with the international standard atmosphere up to somewhere, out of the top of my head, somewhere around 50 kilometers or something. So for all our relevant altitudes, they are now the same. But in the past, it was different, and if you look at the references of Mr. Anderson, he used the book of 1959, and then the US atmosphere was very different from the international standard atmosphere. Not for the first layer, but already this number 20 is different. In his case, it's 25. So do not use those, and also be aware that if you make problems out of Anderson, you might get a different answer if you go above 20 kilometers compared to the ones that he gives. We use always the standard atmosphere, the international standard atmosphere, which is used in avionics and in aeronautics nowadays, ISA, as it's called. So let's go to the first layer. We have, to which altitude do we have to go here in the first layer? What is our H1? 11 kilometers, indeed. We have to go 11,000 meters. We have to go through the whole layer. So the first step that we have to do is to calculate the density, temperature, and pressure at 11 kilometers. So what do we have? We have the starting values. P0, Pascal. We have the rho 0, 1.225. We have the zero temperature, 288.15 Kelvin. We have the lapse rate A, which is? Yes, so it's a decrease, so we had to have the minus 6.5 Kelvin per kilometers. And if we want to use it in the formula, we have to use minus 0.6005 Kelvin per meters. So then we have to go to an altitude H1 of 11 kilometers. So what's the first thing we will do? What's always the first thing we can calculate, because it has the most simple formula? Temperature. So, temperature T1 is T0 plus H times A is 288.15. Somebody has a calculator here? Times 11,000. This should give us the temperature in Kelvin. How cold is it 11 kilometers up? Say again, 2.6. 2.16, okay, sorry, 2.65, okay, Kelvin. Then we can calculate the pressure. By filling in the value of T1 over T0 minus, we use 9.81 for G. Let's add that here on the top because it's also something we use. And for R we use 287.0. Minus 0.0065 times 287. Well, the easiest thing now to avoid problems is to first calculate the exponent and then the fraction and then multiply it by P0. So what is the exponent here? Somebody calculate 9.81 divided by minus 0. Can somebody calculate this? 0.223. That somehow doesn't seem right. It should be somewhere in the order of 4 or 5. 5. Only the exponent. Only the power. I don't have it here. Okay, it's 5.25 and then 9. Okay. And the fraction, and then we have to multiply it by 1. Well, I have the end result here. But if somebody can calculate with me, this is this one, 0.22. .75. We need a few more digits, but you'll keep them in the memory of your calculator. And then the overall result. Now it should be something like 22,000 and then some 614 right here. Okay. So you see, it's easy to make a mistake with these calculations. So break them down in steps and then make the step. So does it seem right, the order of magnitude to us? Yeah, it's like 23% of what we had on sea level. And we are a bit higher than 10 kilometers. And as a sort of reference, I always keep it out of the top of my head. At 10 kilometers, you have only 25% of the air pressure, roughly order of magnitude. So then, how do we calculate the air density? The density we can calculate by just using rho RT, and then saying rho is P divided by RT. So we had, what was the number? 22614 divided by 287 times the temperature, which we also had calculated, 216.65. And this should give the density, rough order of magnitude should be 3636 kilogram per meter cubed. So this is also indeed in the order of around 25%. They don't differ that much, the P and the density, and at least it goes down from 1.225 to 0.36. So that seems about right. So this is our rho 1 and P1, and they now become our new starting values for the next layer. So they now suddenly are our P0, which is 22614. Our rho 0 is now 0.3636. And our T0 is now, we're going to step into the next layer. So what is the next layer? That was very quick. I'll get back to it in a second, no problem. So in the next layer, we see there a constant temperature. So there we use the other formula, the simpler ones. So there we use for P1 over P0. What was it again? Which formula do we need now? The one with the E power, indeed. E this one, right? And there we have to think, what is our H1 and what's our H0 now? H1 20,000 and H0 is now 11,000. So the difference is 9,000. So we can calculate this by e to the power minus 9.81 divided by 287 times the temperature, which is the same for the whole layer, times 9,000. And this times the starting pressure, 22614. Yes? Yes, that's another way. Actually, I do prefer that method, but because I just used 1 and 0. But a better way is indeed to step through from P0 to P1 and then make the fraction P1, P2, and then P3, P2, and P4, and keep numbering. That's even better. That's right. So this one ends up really going down quickly now, I think. 5,466. Okay. And the row 1 or 2, if you continue numbering, should then be already way less. 8, 7, 8, 9 kilogram per meter cubed. And this we can again calculate with simple gas law. So even though we derive the formula for rho and for pressure in the fraction, often you only use one of them, and then you use the gas law to calculate the other. So now we are at what altitude? At 20 kilometers. Still a bit to go. We want to arrive at the altitude of Mr. Kittinger. Next step is, well, we're lucky that we're just underneath the 32 kilometers. That saves us one part of the calculation. So the next H1 or H3 would be, if we use H0 as our 20. Yeah, I'll have to change screens. H1 is now 31,300. T0 is our 216, the constant temperature of the previous layer. P0 is now our previous pressure, which was 5,466 Pascal. And rho 0, if we need it, is 0.08789 kilograms per meter cubed. So the next layer is again a gradient. And we have to see what the value of A is. And there we see that the A is now positive. And it's Kelvin per kilometer. So A is now 0.001 Kelvin per meter. Yes? Heard a question? Starting of a question at least? No. So we do not step through the whole layer now. We go now to our target altitude because it is within our current layer. We now use the formula for the gradient layer, which is T1 times T0 divided by T0. We first have to calculate T1, that's right. So first we have to calculate T1, which is T0 plus H, 8 times H, which is 216.65 plus 0.01 times the delta H, it should be, because we have to start from the base of the layer. So we have to subtract 20 kilometers, so that's 11,300. Which is, you see, should be about 11.3 degrees, right? So we can do it off the top of our head, but I'm going to look anyway. $22795, indeed. So by filling in the different values, we now get 227.95 divided by 216.65, 9.81 divided by positive number this time, and this times our P0, because I've left it out on the left side, 5466. And this gives us, if you would calculate it, I did somewhere, 961.4 is what you should get if you calculate this. Rho 1 is P1 divided by R T1 is 0.01469 kilograms per square meters, per cubic meters. So these are the values that we then have at Kissinger's altitude. Before I box it, I should reduce it to the significant numbers that we got and that we have, but I'll leave that for now. So this is the end result. So let's look at the numbers. Why was Mr. Kittinger moving as he was, as if there was no air? Well, because there was a pressure which is less than, less than 1,000. So less than 1% of the air pressure here. So 99% vacuum. The air density was even less, it was 0.01, while on sea level we have 1.225. And the temperature was not the worst, because it was increasing a little bit, but still quite cold, minus 50 degrees roughly, is the temperature that he needs to protect himself against. So this is when, apparently, what makes a finger double its size, if these are the circumstances, as we know now from empirically. So these are the kind of calculations you need to be able to do yourself. So if you have any questions, please ask. Yes? Say again? A bit, could you keep it quiet? The previous page? Yes? Shh, could you keep it quiet? I can hardly hear the question, so please keep it quiet. It's a good question. Do we need to know the different layers by heart, or do we get a table? You will get a table. So you will get a table with the information on the layers and the value of A. The only thing we want from you is to understand it. You don't have to remember all the numbers, not even the sea level numbers, though it helps. In general, you need to know those to get a feeling for whether numbers are right. But we will give every constant that you need or any definition of the standard atmosphere that you need. You will get in the exam. So you don't have to know those by heart. Yes? Could you use the P0 from the layer, from the table, you mean? Yeah, but we won't give that table that far on the exam. So you could learn them by heart to check your calculations, but we want to see that you can calculate this, because these are relatively simple calculations compared to what you get later in aerodynamics. So they are a good practice to show, to do it. And you should be able, as an aeronautical engineer, to get roughly on the back of the envelope, do some calculations that give you the air density at altitude. Because we have looked at the pressure a lot, but in fact it's the air density that you will use most of the times at altitude. Okay. So this was basically what we needed to cover today. Last time we already did the hydrostatic law. So I'll quickly go to the homework. You will find all the derivations also in the handout and in the book. I want you to check the problems, to try the problems of chapter 3, 3.1, 3.3. They talk about the formula of Toussaint. Remember, that is the decrease of temperature for the troposphere. That's called the formula of Toussaint. Also study section 3.3, or, depending on what you prefer, the last page of the handout that I gave today. I personally thought it was not that clear in the book, so I made a derivation which looks a bit different. But it looks at the geometric versus the potential altitude. And try that as a derivation yourself, and check whether you understand what's being done on this handout. And I will put the answers to the problems on the Blackboard side again. So that's it for today. Next time we will look at Mr. Sinke, will be the lecturer, and he will look at the different forces on an aircraft and focus on the lift and drag force. And there you will also see why we need the air density that often. So, see you next time.
Please visit our OpenCourseware website for more information. See you at our next podcast.